Hello everyone, this is Chengzhi Wu from Karlsruhe Institute of Technology, Germany. It is my pleasure to present our work of Sim2real Transfer Learning for Point Cloud Segmentation, an industrial application case on autonomous disassembly. The AgiProbot project aims for auto-detection, tracking and disassembly of end-of-life products. To be specific, in our current experimental setting, we work on small electric motors used in vehicle manufacturing. Universal method needs to be developed to deal with various types of motors, including the ones with unseen specifications. However, we are only provided with a handful of motors with only few different product specifications. The variance of data is actually not sufficient for training with machine learning methods, especially those deep learning-based ones. To deal with this problem, the Sim2real transfer learning method is applied. Here is the overall framework of our method. First, synthetic point cloud data is generated and pre-processed. It is used for the pre-training of the segmentation network. Then, a very small amount of real-world data is collected, labeled, and used for network fine-tuning. With the fine-tuned network model, we can get good online segmentation results. Finally, product-important information, such as the 6D information of screws, can be provided with post-processing operations. Based on the motor templates we have currently, we created a Blender add-on named Motor Factory, which can generate motor mesh models with a variety of specifications. With those mesh models, corresponding synthetic images and point clouds can be generated in a Blender scene. Note that all semantic labels are generated automatically. No manual labeling is required. We hereby show some results from our experiments. From the table, we can clearly see that using the Sim2real transfer learning with 2 steps of pre-training and fine-tuning improves performance drastically. Some qualitative results are also provided. From it, we can observe that direct training on real-world data performs decently on most points but not so well on tail categories. With the additional pre-training on simulated scenes and fine-tuning the model on real-world scenes, much better segmentation result can be achieved, especially for the tail categories. An ablation study on the augmentation strategies is additionally provided. The imbalanced learning problem is also studied. Here, 4 strategies are proposed. The first one is sample region restriction, which is the crop operation we have applied all the time. The second strategy is focused sampling for tail categories, which means we sample more points on tail categories. The third one is weighting category loss. And the last one is a patch-based attention network. Its key idea is to force the network to learn a same number of kernel points for all categories by using an additional kernel loss. Experimental results are given on this slide. From it, we can observe that the focused sampling strategy always leads to a worse performance. The loss weighting strategy improves the performance on synthetic data but degrades the performance on real-world data slightly. On the other hand, our proposed patch-based attention module improves the performance on both steps. To give better insights of our proposed module, learned patches of some subpoint clouds are visualized. It shows that our method forces the network to learn patches around boundaries or other informative places. We hereby show some post-processed results with our design GUI. Not only the segmentation results, screw 6D information can also be provided with post-processing operations. To conclude, in this work, we present a detailed systematic pipeline for an industrial application case where real-world data is limited, from generating a synthetic dataset, to transferring the pre-trained model to real-world data, and to an ablation study of augmentation operations, with the imbalanced learning problem discussed. For future directions, we would like to try other network backbones, as well as investigate more attention-based learning methods for point cloud data. Thanks for watching.